1,000 kilometers per hour. From Shanghai to Hangzhou in 9 minutes, China's first hyper-high-speed rail is coming.
During rush hours, who needs a car to work or any destination if you have the world's fastest high-speed train around? China got your back. A record-breaking train is about to drop jaws and leave you in total surprise that you might consider moving to where it's going to be launched. Still couldn't believe? Time to meet the world's fast, the furious, and the most powerful train ever created. Trains. Now and in the past. Picture this. China is currently working on a revolutionary train that could soar to speeds of 1,000 kilometers per hour or 621 miles per hour. This incredible speed means you could travel from New York to Los Angeles in just over 2 hours. For comparison, Japan's renowned Shinkansen bullet trains typically cruise at around 200 mph or 320 kilometers per hour.
Dude. Holy shit!
While the fastest operational magnetic levitation, or Maglev train, the Shanghai Maglev, reaches a maximum speed of 268 mph, or 431 kilometers per hour. Now, imagine a train that more than doubles those speeds, outpacing many commercial jets that fly at about 575 mph, or 925 kilometers per hour. Just think, a trip from New York to Chicago could take only 90 minutes. Currently, that journey takes about 12 hours by train or 2 hours by plane, not to mention the time spent navigating airport procedures. In today's fast-paced world, we constantly seek ways to enhance speed, efficiency, and connectivity. We've evolved from horse-drawn carriages to automobiles, from propeller-driven planes to jets, and now we stand on the verge of a breakthrough that could render our fastest trains obsolete. Enter the T-Flight Maglev vacuum train, a groundbreaking innovation set to transform our understanding of high-speed travel. But before we get into more details, let's make a super brief look back to where it all started. Trains have played a pivotal role in shaping human civilization, revolutionizing transportation, trade, and travel. From their humble beginnings in the early 19th century to the cutting-edge Maglev trains of today, the evolution of trains mirrors the progress of technology and human ingenuity. The story of trains begins in the early 19th century with the invention of the steam locomotive. The first full-scale working railway steam locomotive was built by George Stephenson in 1814, but it was his locomotive, Rocket, introduced in 1829, that truly set the stage for modern railways. The success of Rocket, which could reach speeds of 48 kilometers per hour, 30 miles per hour, led to the construction of the first intercity railway between Liverpool and Manchester in 1830. Steam engines were a revolutionary leap forward, enabling the movement of goods and passengers at unprecedented speeds. Railroads soon became the backbone of industrialized nations, facilitating the transport of coal, steel, and other materials critical to the Industrial Revolution. By the mid-19th century, rail networks had spread across Europe, North America, and parts of Asia, transforming economies and societies. And then the transition to diesel and electric trains, just as fast. By the early 20th century, advancements in engineering and technology led to the decline of steam-powered locomotives. Diesel engines, introduced in the 1920s, offered greater efficiency, reliability, and lower operating costs. Meanwhile, electric trains, which had been experimented with as early as the late 19th century, began to gain traction. The first practical electric railway, the Berlin Stadtbahn, was introduced in Germany in 1881. Electric trains were especially popular in urban and suburban areas due to their clean operation and ability to handle frequent stops. By the mid-20th century, countries like Japan and Switzerland were pioneers in adopting electric rail systems for both commuter and long-distance travel. We're now entering the age of high-speed rails. The introduction of high-speed rail marked another major milestone in the history of trains. In 1964, Japan unveiled the Shinkansen, or bullet train, which could travel at speeds of 210 kilometers per hour, 130 miles per hour.
on which it has reached 150 miles an hour on a trial run.
This innovation not only reduced travel times dramatically, but also set the standard for efficiency and safety in rail transport. Other countries soon followed suit, with France introducing the TGV, train à grande vitesse, in the 80s, and Germany launching the ICE, Intercity Express, in the 90s. High-speed rail became a symbol of modernity and a vital component of transportation infrastructure in Europe, Asia, and beyond. Trains have not only transformed how we move, but also how we live, work, and connect with one another. As technology continues to advance, the future of trains promises to be faster, greener, and more integrated than ever before. Trains remain a cornerstone of modern transportation, carrying the legacy of centuries of engineering brilliance into the future. The marvelous Maglev train. The Shanghai Maglev, also known as the Shanghai Transrapid, is a groundbreaking high-speed train that represents a pinnacle of engineering and innovation. Opened to the public in 2004, this Maglev train is the fastest commercially operational train in the world, reaching speeds of up to 431 kilometers per hour, 268 mph, connecting Pudong International Airport to the Longyang Road Station in Shanghai. The train covers a distance of 30.5 kilometers in just over 7 minutes, making it a technological marvel and a symbol of modern transportation. What's the technology behind the Shanghai Maglev? The Shanghai Maglev operates using magnetic levitation, a system that eliminates the need for wheels by using powerful magnets to lift and propel the train. This design drastically reduces friction, allowing for incredibly smooth and efficient travel at high speeds. The train employs German Transrapid technology, a system developed by Siemens and ThyssenKrupp, which ensures precision, safety, and reliability. Unlike traditional trains that run on tracks, the Shanghai Maglev floats 10 millimeters above the guideway. The magnets not only lift the train, but also stabilize and propel it forward using a combination of attractive and repulsive forces. This results in a quiet, vibration-free ride that is both comfortable and futuristic. The Shanghai Maglev's most notable achievement is its speed. During a demonstration run in 2003, it reached a top speed of 501 km per hour, 311 mph, though its operational speed is capped at 431 km per hour for safety and efficiency. This makes it the fastest commercial train in operation, outpacing even Japan's famous Shinkansen and other high-speed rail systems. The train's design prioritizes passenger comfort and safety. With a sleek, aerodynamic exterior and spacious, well-appointed interiors, it offers a premium travel experience. The system is also remarkably punctual, with a 99.9% on-time performance rate, demonstrating the reliability of Maglev technology. The Shanghai Maglev has significantly enhanced connectivity in Shanghai, reducing travel times and easing congestion. By linking Pudong International Airport to the city center, it has improved accessibility for both residents and international travelers, boosting the city's status as a global hub. Environmentally, the Maglev system offers several advantages. It produces lower greenhouse gas emissions compared to traditional high-speed rail or short-haul flights. Its energy efficiency, combined with the lack of direct emissions during operation, makes it a greener alternative in the push for sustainable transportation. Despite its many advantages, the Shanghai Maglev has faced criticism, particularly regarding its high construction costs. The project cost approximately $1.2 billion, a figure that has raised questions about the financial viability of similar Maglev systems in other regions. Additionally, its relatively short route limits its utility, leading to debates about whether the investment was justified. Noise pollution during operation has also been a concern, particularly in areas near the track. While the train itself is quiet for passengers, the external noise generated at high speeds has drawn complaints from nearby residents. The Shanghai Maglev has paved the way for future developments in Maglev technology. China has plans to expand its Maglev network, including proposals for long-distance routes that could rival air travel in terms of speed and convenience. Other countries, inspired by Shanghai's success, are exploring the feasibility of implementing Maglev systems to modernize their transportation infrastructure. The Shanghai Maglev is more than just a high-speed train. It is a symbol of technological ambition and progress. By demonstrating the potential of magnetic levitation, it has set a benchmark for innovation in the transportation industry. While challenges remain, the Shanghai Maglev continues to inspire the development of faster, greener, and more efficient modes of travel, shaping the future of global transportation. Speaking of future developments, that future is now. It's as if you've watched the Meg movie, but next you discover an even faster, bigger, and better Meg, and that's the T-Flight Maglev vacuum train. The fastest train ever. Today, China's Aerospace Science and Industry Corporation is making waves in the transportation sector. They're not merely looking to enhance train speeds. Their goal is to completely transform our understanding of ground travel. The innovative system they are working on aims for astonishing speeds of 1,000 kilometers per hour, almost reaching the speed of sound. To accomplish this, they are merging two groundbreaking technologies: magnetic levitation and vacuum tubes. You might wonder, isn't this similar to the Hyperloop concept that Elon Musk has been promoting? The answer is both yes and no. While both systems strive for ultra-high speeds within low-pressure environments, their operational mechanisms differ significantly. But more on that later. Consider this. What is the primary factor that hinders vehicle speed? Air resistance. As speed increases, air acts like an invisible barrier. This is why the fastest trains today max out around 500 kilometers per hour. Beyond that, they are simply battling against the air. The new high-speed train operates in a low vacuum setting, which significantly minimizes air resistance, enabling those remarkable speeds. So, what is Maglev technology? Maglev, short for magnetic levitation, is a transportation method that utilizes strong magnets to lift and propel trains, eliminating the need for wheels on tracks. These trains glide above a magnetic field. The idea of magnetic levitation isn't entirely new. It dates back to the early 20th century, when pioneers like Robert Goddard and Émile Bachelet first suggested using magnetic fields for transport. However, it has only been in recent years that we've seen it come to fruition. Now, let's delve into how this system functions. Conventional maglev trains hover about 10 mm above the track, but this new design elevates the train by 100 mm, 10 times higher. This greater distance reduces interference and enhances stability, allowing for smooth operation at extraordinary speeds. The trains are being constructed using carbon fiber materials, which help to minimize weight while ensuring structural strength. This initiative isn't solely focused on speed. It's about achieving speed in an efficient manner. The superconducting maglev technology being employed is particularly innovative. When specific materials are cooled to extremely low temperatures, they transform into superconductors, allowing them to conduct electricity without any resistance. This significantly enhances the efficiency and stability of magnetic levitation. You might wonder, does this actually function in practice? The good news is that testing has already commenced, and the outcomes are encouraging. In Shanghai province, a 2-kilometer test track has been established. While 2 km may seem modest, it provides ample opportunity to evaluate all essential systems. The test results closely matched their theoretical expectations. Calculating the feasibility is one thing, but witnessing it in action is another. During the trials, they concentrated on several critical factors. First, precise navigation. At such high velocities, even a minor deviation could lead to disaster. The system must ensure the train remains on its designated path with remarkable accuracy. Next, stable suspension is vital. The train must keep a steady height above the track, free from any wobbling or variations. This is essential for both passenger comfort and safety. Lastly, safe stopping is crucial. While achieving high speeds is impressive, the ability to halt safely is equally important. The tests confirmed that the system could bring the train to a controlled stop from high speeds. These trials have validated that the fundamental concept is sound. The next phase involves expanding the system for longer distances. The 1,000 km/h train in China represents a bold step into the future of transportation. By combining seriously advanced technologies, it promises to redefine how we travel, making long distances feel shorter and fostering greater global connectivity. While challenges remain, the project's potential benefits, in terms of speed, sustainability, and economic growth, are too significant to ignore. As China continues to push the boundaries of innovation, this train may soon become a symbol of what the future holds for human mobility. Economic impact. China's ambitious project to develop a train capable of traveling at 1,000 kilometers per hour or 621 mph is not just a marvel of engineering. It also promises to reshape the nation's economy. By combining cutting-edge magnetic levitation technology and vacuum tube systems, this high-speed train has the potential to create profound economic benefits, from boosting regional connectivity to reducing transportation costs and fostering sustainable development. One of the most significant economic impacts of the 1,000 km per hour train lies in its ability to create one-hour economic circles. These are regions where cities separated by hundreds of kilometers are connected within an hour, effectively shrinking geographic distances. For example, a journey between major urban hubs like Beijing and Shanghai could be reduced to under 2 hours, compared to the current 4 to 5 hours by high-speed rail or over 2 hours by plane, when accounting for airport logistics. This enhanced connectivity will stimulate regional integration by encouraging business collaboration, investment, and tourism. It could also promote balanced economic growth, enabling smaller cities and rural areas to benefit from closer ties to major economic centers. As industries expand beyond traditional hubs, the economic disparities between urban and rural regions may diminish. The 1,000 km per hour train promises to revolutionize commuting and travel for businesses and individuals. With faster and more reliable transportation, businesses can operate more efficiently, as employees can travel between cities for meetings or collaborations within a single day. This could lead to increased productivity and more dynamic business operations. For individuals, the ability to live in one city and work in another without sacrificing significant time in transit could reshape housing and labor markets. People may choose to reside in more affordable cities while working in higher-paying urban centers, thereby redistributing economic activity across regions. Speaking of work, the creation, operation, and maintenance of such trains alone will provide thousands of jobs. The construction phase of the 1,000 km per hour train will require a significant workforce to build the necessary infrastructure, including vacuum tubes, elevated tracks, stations, and other essential components. Skilled laborers such as engineers, architects, and construction workers will be needed to design and construct these structures, while laborers will be required to handle the physical work. Additionally, the manufacturing of materials such as superconducting magnets, carbon fiber components, and other specialized elements will create jobs in factories and production plants. The development and implementation of such advanced technology demands a highly skilled engineering workforce. Scientists, engineers, and technicians specializing in fields such as superconductivity, Maglev technology, and vacuum systems will play a pivotal role in designing, testing, and refining the train's systems. This project will not only create jobs in the immediate term, but also offer long-term career opportunities in research and development, fostering innovation in transportation technologies. While the initial construction costs for the 1,000 km per hour train are expected to be substantial, the long-term savings in transportation costs could be significant. High-speed maglev systems are more energy efficient than traditional rail or air travel, reducing operating costs over time. Additionally, the train's ability to carry large numbers of passengers at high speeds could lead to economies of scale, making it a cost-effective mode of transport for both passengers and freight. For industries that rely on fast logistics, such as e-commerce and manufacturing, the train could serve as a critical asset. It would allow goods to be transported across the country quickly and efficiently, reducing delivery times and enabling businesses to better meet consumer demand. From an economic perspective, the environmental advantages of the 1,000 km per hour train also carry financial implications. Air travel is a major contributor to greenhouse gas emissions, with short-haul flights being particularly inefficient. By replacing these flights with a cleaner alternative, the train could significantly reduce carbon emissions, contributing to China's sustainability goals. Lower emissions translate to reduced costs associated with environmental degradation, such as healthcare expenses linked to air pollution and the economic impacts of climate change. Additionally, the train's energy efficiency could help reduce the nation's reliance on fossil fuels, lowering energy costs in the long run. Let's pump the brakes for a second. It's a big plan. Therefore, it's got to face a big challenge. Despite its potential, the economic benefits of the 1,000 km/h train come with significant challenges. The cost of building and maintaining the infrastructure, including vacuum tubes and maglev systems, is expected to run into hundreds of billions of dollars. Funding such projects requires substantial investment from both the government and private sectors. While the concept is undeniably exciting, there are substantial hurdles to address. The costs associated with infrastructure are staggering. Constructing low vacuum tubes over extensive distances is far from affordable, and merging this new system with current rail networks presents its own set of complexities. For context, the expense of developing traditional high-speed rail lines can vary between $17 million and $170 million per kilometer, influenced by the landscape and other variables. A maglev system housed within a vacuum tube would likely incur even higher costs, potentially reaching hundreds of billions of dollars for just one long-distance route. Safety is another vital factor to consider. At such high velocities, even minor problems could lead to significant repercussions. Therefore, the emergency protocols must be impeccably reliable. However, China has a track record of successfully executing large-scale infrastructure projects. By leveraging public-private partnerships and international collaboration, the country could mitigate the financial burden and ensure a return on investment through increased economic activity and improved quality of life. The development of the 1,000 km/h train could also position China as a global leader in high-speed rail technology. By exporting this technology to other countries, China could open new markets for its engineering expertise, creating additional revenue streams. This leadership would enhance China's influence in the global transportation sector, further solidifying its role as an economic powerhouse. The 1,000 km/h train in China is more than a transportation project. It is a catalyst for economic transformation. By connecting regions, boosting productivity, reducing transportation costs, and promoting sustainability, this innovation has the potential to reshape China's economic landscape. While challenges remain, the long-term economic benefits could far outweigh the initial costs, making the 1,000 km/h train a symbol of progress and prosperity for the future. However, China is not the lone competitor in such massive high-speed trains vision. Other countries are also developing similar innovations, although the pace is a little slower. The rest of the world. The race to develop faster maglev, or magnetic levitation trains, is a technological contest that reflects national priorities in innovation, transportation, and economic development. China, Japan, Germany, and other nations are at the forefront of this competition, each pursuing advancements that could redefine high-speed travel. While China's 1,000 km/h maglev train is making headlines, other countries have also made significant strides. Comparing their approaches highlights the unique challenges and opportunities each nation faces in this ambitious endeavor. China has emerged as a leader in maglev technology, driven by its focus on infrastructure development and transportation innovation. Its most notable maglev system, the Shanghai Maglev, has been operational since 2004, reaching speeds of 431 km/h. Building on this foundation, China is now developing a 1,000 km/h train that combines maglev technology with vacuum tube systems to dramatically reduce air resistance. China's approach emphasizes scaling and self-reliance. Initially relying on German technology for the Shanghai Maglev, the country has since developed indigenous systems, such as the Changsha Maglev line. By prioritizing domestic innovation, China aims to dominate the global maglev market, potentially exporting its technology to other countries. Japan has long been a pioneer in high-speed rail, with its Shinkansen bullet train systems setting global standards for speed, safety, and efficiency. Japan's superconducting maglev system, the Chuo Shinkansen, is designed to reach speeds of 505 km/h. Construction is underway to connect Tokyo and Nagoya by 2027, with future extensions planned to Osaka. Japan's Maglev trains utilize advanced superconducting magnets to achieve stable levitation and propulsion. The focus is not only on speed, but also on reliability and passenger comfort. Unlike China's 1,000 km/h goal, Japan's strategy is more conservative, aiming for incremental improvements within the framework of its established rail infrastructure. Germany is the birthplace of Maglev technology, with its Transrapid system laying the groundwork for many modern designs. While the Transrapid 09 achieved a top speed of 500 km/h, its commercial adoption has been limited. The technology was licensed to China for the Shanghai Maglev, marking Germany's significant but somewhat passive role in the global Maglev landscape. Germany continues to innovate in Maglev technology, focusing on shorter distance applications and urban transit systems. However, the country has not pursued ultra-high-speed trains like China's 1,000 km/h model, largely due to financial and logistical constraints. Have you heard about the Hyperloop? The US is cooking that one. While the US has not developed Maglev systems comparable to China or Japan, it has explored alternative high-speed concepts like the Hyperloop. Proposed by Elon Musk, the Hyperloop envisions passenger pods traveling through near-vacuum tubes at speeds exceeding 1,200 km/h. Despite its futuristic appeal, the Hyperloop remains in the experimental stage, with significant technical and regulatory hurdles to overcome. Meanwhile, some states have shown interest in Maglev projects, such as a proposed Maglev line between Washington, D.C. and Baltimore, which would use Japanese technology. So here are the differences. China is pushing boundaries with its 1,000 km/h target to leapfrog existing technologies. Japan and Germany prioritize incremental improvements and practical implementation. The US focuses on alternative concepts like the Hyperloop, targeting even higher speeds but with uncertain timelines. China has invested heavily in infrastructure, with government support driving rapid development. Japan relies on its established rail network and public-private partnerships. Germany and the US face challenges in funding and integrating new systems into existing infrastructure. China combines Maglev with vacuum tube systems for ultra-high-speed travel. Japan focuses on superconducting magnets for reliability and efficiency. Germany explores urban applications, while the US experiments with futuristic designs. The competition to develop faster Maglev trains has broader implications for global transportation. China's aggressive pursuit of 1,000 km/h technology positions it as a leader in high-speed rail, potentially setting new benchmarks for speed and efficiency. Japan's and Germany's focus on reliability and urban transit reflects their commitment to practical, scalable solutions. Meanwhile, the US experiments with bold concepts that could redefine transportation in the distant future. As nations refine their approaches, the race for faster Maglev trains underscores the importance of innovation, collaboration, and strategic investment. While each country faces unique challenges, their collective efforts promise to revolutionize how we think about speed, connectivity, and the future of travel. Now, the environment. China's development of this high-speed train is not just a technological leap, but also a significant opportunity to address pressing environmental challenges. As the world grapples with climate change and the environmental costs of modern transportation, this innovative project offers a promising path toward more sustainable mobility. From reducing carbon emissions to enhancing energy efficiency, the environmental considerations surrounding the train's development are vital for both China and the global community. One of the most significant environmental benefits of the 1,000 km/h train is its potential to reduce carbon emissions. The transportation sector is one of the largest contributors to greenhouse gas emissions, particularly from air travel. Short-haul flights, which are often the most polluting form of transportation, emit between 150 and 200 grams of CO2 per passenger kilometer. In contrast, even conventional high-speed rail systems emit only about 20 to 30 grams of CO2 per passenger kilometer. With Maglev trains operating in a low-vacuum environment, the expected emissions will be even lower, making this high-speed train an eco-friendly alternative to short-haul flights. The train could drastically reduce the need for air travel over distances up to 1,500 kilometers, thus significantly cutting down carbon emissions and contributing to China's efforts to reduce its overall carbon footprint. In addition to lowering emissions, the 1,000 km/h train is expected to be highly energy efficient. Maglev technology, which uses superconducting magnets, is inherently more efficient than traditional rail systems due to the reduction in friction. The train operates in a low vacuum environment, which further minimizes air resistance and energy consumption. This makes it possible for the train to travel at incredibly high speeds while using less energy. The integration of renewable energy sources such as solar, wind, or hydroelectric power to operate the system could further enhance its sustainability. By relying on clean energy, China could reduce the environmental impact of the train's operations, helping to achieve its climate goals and setting a global example for energy-efficient transportation. This is music to the environmentalist ears. Another critical environmental consideration is the impact of the train's infrastructure on land use and natural habitats. Constructing the necessary vacuum tubes and maglev tracks over long distances can potentially disrupt ecosystems and wildlife. However, by designing the infrastructure to be elevated and minimizing the land footprint, the environmental impact can be mitigated. Furthermore, careful route planning to avoid sensitive ecosystems and urban areas can reduce ecological disruption. The construction of these systems also presents an opportunity to encourage more compact urban development, as high-speed rail connectivity fosters urbanization that is more sustainable and less reliant on sprawl. This can help protect rural and natural areas from unchecked expansion, contributing to a more balanced relationship between cities and the environment. The environmental advantages of the 1,000 km/h train are not limited to carbon emissions and energy efficiency. They also extend to pollution reduction. Air quality in urban areas could significantly improve as fewer people rely on short-haul flights and cars for travel. Additionally, maglev trains are quieter than conventional trains and airplanes, which can help reduce noise pollution in communities near transportation corridors. The use of advanced materials and more efficient systems can also minimize waste and pollution generated during the construction and operation of the train, ensuring that the environmental footprint of the project is as small as possible. However, the development of such an ambitious transportation system is not without its challenges. One of the primary concerns is the energy demand required to operate the train at such high speeds. While maglev trains are energy efficient, the sheer scale of the project will require a substantial amount of electricity. Ensuring that this energy comes from renewable sources is essential to maintaining the environmental benefits of the train. Additionally, the construction of the infrastructure itself presents challenges, as it can disrupt local ecosystems and contribute to emissions. The production of materials such as carbon fiber and superconducting magnets also involves energy-intensive processes, which must be accounted for in the project's overall environmental impact. Despite these challenges, the environmental potential of the 1,000 km/h train is significant. To mitigate its environmental impact, China could implement strategies such as using recycled and low-impact materials during construction, offsetting emissions through reforestation projects, and integrating renewable energy into the system's operations. By carefully managing these factors, the train could become a model of sustainable transportation, demonstrating that high-speed travel does not have to come at the expense of the planet. Let's watch out until this Maglev 2.0 is out. We'll see you in the next video.